There you go.
Okay. Hi, I'm presenting on the paper Diverse Coral Communities in naturally acidified waters in the Western Pacific region. So in Palau, Rock Island Bays, they have highly diverse coral-dominated reefs that exist under constant low pH and aragonite saturation state. The low pH is caused by calcification by the reefs, CO2 emitted through respiration, and freshwater flow off the land. This is important to study because these levels of acidification are similar to those projected for the Western Tropical Pacific Open Ocean by the year 2100. For the methods, surface water samples were collected at 9 stations along the Palau Reef in the wet and dry seasons from sunrise to sunset and throughout the tidal cycle. The three factors that were examined to assess the health of the coral communities along the natural acidification gradient were the percent of live coral cover, the coral diversity, and the coral taxonomic richness. Contribution of various factors causing the low pH is determined by comparing water samples from offshore and the reef sites. The seawater CO2 system for the sample sites was calculated from total alkalinity, TA, dissolved inorganic carbon, DIC, and salinity and temperature. Calcification decreases total alkalinity and dissolved inorganic carbon by a ratio of 2:1, and this allowed researchers to estimate the net contribution of calcification to the lowering of aragonite saturation state as seawater moves across the barrier reefs into the bays. They found out that the surface water pH, carbonate ions, and aragonite saturation state decreased as they moved inland, and calcification, respiration, and runoff dilution appear to be the main factors of the count. And here is a map of Palau, and these are the sites that they took samples from, as you can see. Okay. These are along the barrier reefs here and here, and then as you move further inland in sites 7, 8, 9, these are within the Rock Island Bay, and as you can see from the colors, they also have the lowest aragonite saturation state. This graph shows the aragonite saturation state compared to the distance from water offshore, so as you go this way, it's more inland. The yellow shading represents the aragonite saturation state average in 2000, and the orange is the projected aragonite saturation state in 2100. As you can see, in the sites 7, 8, 9, which were within the bay, they're most closely related to the projected aragonite saturation state, and they're also closest to the shores. And then again, this one is comparing the pH to the distance from offshore waters, and once again, the sites 7, 8, 9 in the bay are more closely related to the projected values of the pH in 2100. They found out that 68 to 99% of the difference in aragonite saturation state between offshore water and the reef water was driven by calcification of the organisms in the reefs. So this graph is showing the calcification relationship between TA and DIC, and the above the red line are the normal values, and the below the red line indicate an additional input of DIC, and as you can see, the sites 7, 8, 9, which were in the bay, had an additional input of DIC. So again, in the barrier reef and exposed sites, which were sites 1 through 6, photosynthesis and respiration were approximately balanced, and so they had a significant influence on mean DIC and aragonite saturation state. However, in the sheltered rock islands, or the Rock Island Bay, they found that there was an additional input of DIC, and therefore, it may be because of respiration occurring in the bays, and or an input of groundwater with elevated states of CO2. Also, residence time within the bays is much longer than in the exposed sites on the barrier reefs, which would allow calcification and respiration to bring the aragonite saturation state to such low levels. Now regarding coral system health, the Rock Island Bay sites, hard coral diversity is high compared with the barrier reef and more exposed sites. Coral cover in the Rock Island Bay sites was also significantly higher than the average in the whole tropical Western Pacific, and which is reveals patterns that are unlike those compared to other naturally acidified water. This graph is showing coral system health in percent coral cover, and as you can see, or compared to the aragonite saturation state, and sites 9 and 8 within the bays, even though they had a low aragonite saturation state, they had a higher percent coral cover compared to the other sites along the barrier reefs. This graph is showing coral diversity compared to the aragonite saturation state, and then once again, sites 9 and 8 are higher than those in the barrier reefs and exposed sites, and the triangles are showing coral richness, the taxonomic richness, and the blue squares are showing the diversity. Within the sites of Palau, the average hard coral richness was greater in the bay than the barrier reefs, and compared to other naturally low pH sites, the coral cover and richness is greater in Palau than anywhere else, including the CO2 seeps of Papua New Guinea. Natural acidification is due to a combination of processes, and in the other sites it's due to usually one factor, which is the absorption of excess CO2, whether it's from the vent sites or an influx of CO2 from groundwater. Also, the coral communities in Palau have been existing under these conditions for thousands of years, and so they had time to adapt, and which is unlike those in the other low pH sites. And in conclusion, Palau is unique in its ability to support such diverse and extraordinarily dense coral communities despite the harsh seawater chemistry. And by comparing conditions and community responses in the naturally acidified waters, we can learn more about how to enable healthy coral communities to persist under ocean acidification in the future. And well, that last picture is a picture of mankind.